Greetings, everyone. Welcome back into the world of calculus. Time to take a sidestep for a moment and sum up all of the things we've done in this first big unit. We want to talk about reviewing for a first test in a calculus course. So my first disclaimer, as usual with all of these reviews, is that you shouldn't just study these particular problems. Don't look for patterns. You should try to work the problems before I get done with them, maybe even. You should try to get the skills down that these problems represent. You need to practice the skills themselves in order to do well on any math test. These are just examples taken from tests that I have given in the past. So let's look at some of the topics that are involved here. All right, so we have all of the things that deal with beginning to learn limits, right? Evaluating limits at different levels, whether it be substitution or having to algebraically manipulate them or having to do a chart. And then eventually being able to use what we call all the limit laws and splitting up limits into pieces if necessary, and even some of the specialized limits that you need to have memorized usually. Under the laws here, talk about special limits too. Okay, we also need to look at being able to prove that a limit actually does give the value that it's supposed to at any particular point using the epsilon delta definition. Honestly, typically I use this more as a bonus feature, but that's not a promise on any, sort of level that anybody out there couldn't put this on a test of this caliber. Continuity, of course, leads straight from limits, and being able to identify where a discontinuity is and the type of discontinuity that is being presented. And then, of course, to really get into the calculus features here, we start talking about derivatives. Everything on this first unit are derivatives done with the limit definition. No shortcut rules of derivatives whatsoever on this particular test, right? So calculating, of course, using limits, just making a derivative calculation. Being able to talk about tangents to a graph, tangent lines, maybe the slope of one, or maybe actually creating the equation of one. All right, measure of a rate of change and any other application that goes with that idea of measure of a rate of change on a basic definition level. Being able to interpret regions of maybe positive and negative derivative, things like that. Let's start off with some limit calculations. So these are some problems that I've thrown on tests, and I don't allow any real shortcut rules as far as the limits are concerned. For those of you that have skipped ahead or taken some calculus before, no L'Hopital's rule is allowed. These are plain straightforward. You need to know the couple of little special limits that we've shown you, and you need to know how to break these down and just calculate the limits the old-fashioned way, the basic definition way. Okay, so let's start at the top here. The limit as x goes to 0 of sine x cosine x over x times 1 plus cosine of 5x. Now, just because something has a bunch of pieces, don't let it throw you off. I already see one limit in there that's a special one that I can get rid of really quickly, right? I can split this into the limit as x goes to 0 of sine x over x. And we know that one, right? That's a special limit, right? That one's 1 times, and then I've got the limit as x goes to 0 of the rest, the cosine x over 1 plus cosine 5x. With this one, you can just do some substitution. If you plug in 0, check it out, right? cosine of 0. So I've got 1 times cosine of 0 is 1. 1 plus cosine of 5 times 0, right? That's still cosine of 0, which is 1. So I end up with a final value of 1/2. Here, let's separate these a little bit so we don't get these mixed up together. Alrighty, so next, the limit as x goes to infinity of 8 times tangent x. And I threw this one on a test just to see a couple of things. First of all, are you paying attention to what we're really doing the limit of? And secondly, are you familiar with your basic functions? Tangent is a periodic function. Very often, trying to take an infinite limit on a periodic function gives all kinds of problems. Very often that happens. Tangent is no exception. Tangent is that graph that you get the swirl shapes over and over again, right? Swoosh, swoosh, swoosh. But as x goes to infinity, where exactly are you going to land on any of the given periods, any of the given cycles? This one's going to be undefined. Because of that periodic nature of tangent. Okay, next. Limit as k goes to infinity, -6 sine of k over k. And I threw this one in there again on a test to see if you were paying attention. It looks a lot like that special limit that you have to memorize, and people would automatically put 1 times -6. Don't make that mistake. Look, it's the limit as k goes to infinity, not 0, of sine k over k. All right, so the sine portion of it falls into the same trap as the periodic portion of the limit as x goes to infinity of 8 tangent x. Okay? But I'm not as worried about it because I'm going to do this. I'm going to say it's -6 times the limit as k goes to infinity of 1 over k. I'm going to treat this as one separate chunk, just 1 over k right there. And then times the limit as k goes to infinity of sine k. Now by itself, this would really be an undefined limit. But don't forget, this is a limiting process. This is going to be some number for a while until it just becomes undefined because of you can't hone in on a number. But this limit right here, you know this limit is 0. Because I'm letting the denominator become infinitely large while the numerator stays as 1. So I've got -6 times 0 times something, but it doesn't matter. That something is some number between -1 and 1. That's all sine is allowed to put out. It's not like I have infinity times 0. That would be sort of inconclusive, right? I'd have to think of some other way of dealing with that. But this is some number between -1 and 1. No big deal. Times 0. So we get 0. Okay, next. I have the limit as w goes to infinity of this weird radical rational expression. So you need to just really be looking at this expression for those small details. I notice that the w squared and the square root of w to the 4th are around the same strength. They're around the same power. So what I can do is relate the 9 and the 15 somehow to get my answer. And there's all kinds of other little shortcut rules, but let's go through the actual steps here. If I multiply the numerator by 1 over w squared, right, the whole numerator, and then I multiply the denominator by the square root of 1 over w to the 4th. I'm multiplying the top and the bottom by equal values. The square root of 1 over w to the 4th is 1 over w squared. So I'm multiplying by an overall value of 1. However, in the numerator, the w squared is going to wipe out the w squared there, and the w 4th here is going to wipe out the w to the 4th, and then I'll have a bunch of other little pieces that are going to go away. look, this is what happens. I have this limit as w goes to infinity. 9 plus 13 over w minus 1300 over w squared over square root 1297 over w to the third plus 15. So just like over here with this limit as k goes to infinity of 1 over k goes to 0, each one of those other little fraction pieces are also all going to go to 0. This piece is going to go to 0, this piece is going to go to 0, this piece is going to go to 0. All I'm going to be left with is 9 over the square root of 15 from those two pieces. And I'm fine with leaving it there. Some people may want you to rationalize it. If you do that, you'll have to simplify the fraction a little bit too. That sort of thing. Okay? Let's see. Now, limit as x goes to 6 of x to the third minus 216 and x squared minus 2x minus 24. So if I substitute a 6 in the numerator, 6 to the third is 216, so I'm going to get a 0. In the denominator, that's 36 minus 12 minus 24, which is also 0. So I have a 0 over 0 situation. And I'll remember, a lot of times what that means is that I can do some sort of manipulation in there, some sort of cancellation, some sort of elimination to make this thing at some later stage easy to plug into. So let's do some factoring. The numerator is a difference of cubes. So I've got limit as x goes to 6 of x minus 6 times x squared plus 6x plus 36. That's the difference of cubes formula. Divided by, this is just your normal trinomial factoring. I need two numbers that multiply to negative 24 that also add to negative 2. That's going to be x minus 6 times x plus 4. All right. I got rid of my x minus 6's here. Right? I can eliminate them due to division. Those were the pieces that were zeroing out, notice, because 6 minus 6 is 0. So with that out of the way, the rest should be okay to plug in my 6. So the denominator is going to be 10. You can see that right away. The numerator is 36 plus 36 plus 36. Right? So 3 times 36 on that note right there. I did that to help my mental math here. I can reduce this a little bit. 36 and 10 will reduce with a 2. Right? That'll give me 18 here and 5 here. 3 times 18 is 30 and 24 is 54. Fits. All right. Okay. And then the bottom guy here. The limit is h goes to 0 of 1 minus e to the h all over h. Well, if I plug in 0, I've got 1 minus 1, which is 0, and h is 0, so I have 0 over 0. Again, it's one of those times where I have something 0 over 0, and you'd think, oh, well, maybe I can try to reduce it like I did the last one, try to make something eliminate like we did in the last one. Unfortunately, there's nothing to factor here, and there's nothing to eliminate top and bottom. I can't separate it very easily. It's not going to work out very well. This really is simplified. So I've got all the way down to my bottom rung. We're just going to have to chart this one out. Okay, so that's what we'll do now. I've got h values, and let's call them limit values, L values, right? The h is the input, L is the output. A lot of times this would have been x and the L would have been y's, but that's not what we're using here. So I'm trying to approach 0 We probably don't need very many steps, but I'll put 0 here in the middle. I'll just use a couple of steps on each side. Because remember, we're still, pretend like we're taking a test here. So we're trying to do this quick. So if 0's here, let's start with negative 0.01 and negative 0.0001. And then from the other side, we'll do the same thing. 0.01 and 0.0001. So that I'm going in each direction like this, right? We're trying to squeeze into h going to 0 from both directions here. So if I plug in negative 0.01 into this numerator here, that's 1 minus e to the negative 0.01. And I'm going to divide by negative 0.01. So I have negative 0.995. Negative 0.995. Okay, so then we can repeat. We just put in some more zeros. And I get negative 0.99995, like so. Okay. Now I'll just go back and I'll take out the negatives. So here I've got negative 1.00005. And negative 1.005. Now, of course, I've chopped these decimals a bit, but I think this is sufficient enough for us to see the pattern. From the left, the further I go closer to 0 here by plugging in that number, I can see that the output limiting value gets more and more 9s after the decimal place. So if I were to go even closer with more 0s and a 1, I would get more 9s and a 5. So as you can see, this looks like it's approaching negative 1. And it's quite obvious from the other side as well. The more zeros that I put here, this thing gets more and more of a separation between the negative 1 and the 5 in the decimal place. The 5 is eventually going to go infinitely out. Both directions are going to negative 1. The answer here is negative 1 to this limit. Here are some more problems with limits. So I have a piecewise function f of p, and then I want to evaluate one particular p value. The only one that's really kind of special is 5, right? Because that's the split between the two pieces in the piecewise function. So naturally, you'd want to evaluate the limit from the left and the right and see if I can get an overall limit as p approaches 5. Okay, so the limit as p approaches 5 from the left would mean that I would want to take any p values that are less than 5. So the limiting process would bring me on along this curve right here. The lesser values of p would come from this curve. So then I would be very interested in 5 squared minus 3 times 5, which of course is 25 minus 15, which is 10. So there's the first answer. Next, the limit as p approaches 5 from the right would want all of the p values that are greater than 5. Therefore, I would be using this bottom piece here. So I'll be getting 5 plus 4, because I'm plugging in the p value here, which of course gives me 9. Now, since 9 doesn't equal 10, the overall limit as p approaches 5 is going to be undefined. Right? There's no agreement from left and right there. Okay, next. G of x is equal to the absolute value of 2 minus x over 2 minus x. And of course, the interesting point would be at x equals 2. If I try to just plug in 2, I get 0 over 0, and we hope that that means that I can do some sort of manipulation. Sure. Well, from the left of 2. Okay, well, if it's to the left of 2, then that means this absolute value is acting on a negative number there. Okay, if it's, it's working on a positive value there. Because if it's less than 2, right, then anything less than 2 here, 2 minus 1, 2 minus 0, 2 minus negative 1, this absolute value is going to be working with a positive value, which means it's really not going to do anything. Okay, so in other words, this is just going to be 2 minus x over 2 minus x, which is just going to give me a 1. Next, if I go anywhere from the right of 2, now, that means a number greater than 2. So that means the absolute value is going to be dealing with negative numbers. For example, 2 minus 3, 2 minus 4, 2 minus 5. They're all going to be negative numbers. And what do absolute values do? They take the opposite of a negative number. So you end up doing the opposite of whatever 2 minus x is over 2 minus x. Notice that this would simplify to negative 1. The graph of one of these things is actually rather interesting. It's really just two horizontal line pieces, two half horizontal lines that don't meet up because one's at 1 and one's at negative 1, like this. And you don't have a value at x equals 2 in this case. We also don't have a limit value, right? Since 1 and negative 1 don't agree, the limit is also undefined. Okay, switching gears just a little bit here. We can use limits to describe basically the tools to help us get into the graph of these things, right? I'm going to first start with the domain of this function, and then we need to talk about how to describe the asymptotes of this function using limits. So you've probably hit asymptotes in other classes, college algebra, trigonometry, and things like that. And a lot of times what you do is you just list the values. Oh, the asymptote happens at such and such value. Here in calculus, what we want to be able to do is actually use our limit language to describe the asymptote. And so that's what we're going to do here. So start with the domain, right? List the domain here. So the domain is going to be negative infinity to 0 union 0 to infinity. Okay, so think about it. I can plug in any value I want in an exponential and it'll give me a number just fine, right? This is the main piece because this is where x is. That thing's going to work. Subtraction always works. Division always works, except division by 0. Notice if I plug in 0, right, e to the 0 is 1, 1 minus 1 is 0, and that would cause a division by 0. But any other number is not going to do that. So in this case, x equals 0 is the only point that I need to leave out of the domain. So for the domain, I can say that x is some element of these two disjoint intervals. Okay, next, let's talk about the asymptotes. Well, since I have this division by 0, remember division by 0 very often gives us a vertical asymptote. We'll be able to decide that using limits. And then on top of that, I'm going to see if there are horizontal asymptotes by using the negative and positive infinity limits as well. Okay, so let's start with the horizontal asymptotes. The horizontal asymptotes are going to be the limit as x goes to infinity, let's say, of 5 over 1 minus e to the negative x. Okay, so really in this case, all I'm interested in is the exponential, because that's a pretty straightforward limit. The limit as x goes to infinity of e to the negative x. Okay, that means that I have e to the negative x, but then I'm using a very large number for the exponent. So e to the negative infinity, if you will, right? E to a very large negative power is going to get smaller and smaller and smaller. Because remember, the negative power makes you do a fraction with just that little piece. Okay, this value right here is going to 0. So therefore, I have 5 over 1, which is just 5. Okay, so there's a horizontal asymptote. As x goes off to infinity, the function will want to hug the y equals 5 line. Next, what about negative infinity? The limit as x goes to negative infinity of 5 over 1 minus e to the negative x. Let's write something equivalent here, okay? Notice I'm going to negative infinity, and every time I get a larger and larger negative, I'll be approaching and putting a negative for this exponent, okay? So here's an equivalent limit. This is going to be the same thing as if I were to let x go to positive infinity, and my internal function were just 5 over 1 minus e to the x, like that. Okay, so if I let x go to infinity of e to the x, this is going to become infinity, right? That is an unbounded function. The exponential on the infinite side like that, e to a very large number, is unbounded. So basically goes to infinity also. 1 minus infinity, this denominator is becoming one big negative infinity. Okay, so here, the limit of this guy right here is going to be negative infinity. Just the limit of that portion. Now, what does that mean for the whole thing? Right? Well, that means, oops, wrong color. Trying to stay with blue here. This means that I'm going to 0. Because the bottom is becoming infinite. Next, let's talk about the vertical asymptote. There's only one vertical asymptote here, but it takes two limits. Because remember, vertical asymptotes can take on a couple of different formats. I can have the vertical asymptotes like 1 over x squared, where it's a volcano shape and they match. Or I can have the vertical asymptotes where it's like the baseball crosshatch shape, like 1 over x. Okay? So what I'm going to need to do is I'm going to need to take a limit from the left of 0 and a limit from the right of 0 to determine the vertical asymptote nature. So I need a limit as x approaches 0 from the left of this, and a limit as x approaches 0 from the right of this, 1 minus e to the negative x. Okay, so from the left, what I have is negative numbers, right? The left of 0 are very small negative numbers. I'm going to get a negative when I plug them in, and I have e to a very small negative number. Now, of course, that's going to be some root of e, but it's still e to something a little bit bigger than 0 because of the double negative. Since it's e to something a little bit bigger than 0, then this value is going to be a little bit bigger than 1, basically. Okay? And this thing is going to try to approach 1 minus 1. It's like a division by 0. Okay? But what's happening is this piece right here is going to be slightly larger than 1. So I'm going to get a very, very small negative number in my denominator here, which means that this eventually is going to go to negative infinity. Let me say all that again. Because the size, when I plug in negative values here, I'm doing e to a very small number. It's going to be slightly bigger than 1, but it's slowly approaching 1. I'm eventually going to get a 0 denominator, which means I know it's infinity, right? But which is it? Is it negative or positive infinity? And it turns out to be negative because this calculation is always going to be slightly bigger than 1, but less and less so as I get closer. So the denominator is always negative, right? So 5 over a very small negative number eventually is going to give me negative infinity. What about this side? I have a positive number here. When I plug it in, I have e to a negative number, okay? Which is going to make it a very, very small number. The e to a negative power makes the value shrink smaller and smaller and smaller. It's always going to be less than 1, okay? But it's trying to get closer to 1, but it's less than 1 at every step. So my denominator stays positive in that case. This will be infinity. If you're still not quite seeing what I'm saying by arguing about positive and negative numbers here, make a chart of these two limits. Find numbers that are closer and closer, and you'll see what's actually happening with these patterns of negatives and positives, and you'll see why those values end up being the way they are. So I've actually described a single vertical asymptote here, but it's a split one, right? I've got one side going down, I've got one side going up. And then I also have described two different horizontal asymptotes, one on the right-hand side and one on the left-hand side. And that actually gives you a pretty good overview of what the shape of the graph needs to look like. So just a little bit more on limits. This is the kind of problem that I usually expect as more of like a upper end or maybe even a bonus type of question in my class, just because of the level that we're at. And you really need to get your language perfect for one of these. So this is one of those things where you can push yourself to get really good at understanding what the language is saying inside of a limit. But at the same time, if it's at the cost of some of the more important basic skills, then you should focus on this after. But this is still a very important concept, what a limit actually is. So I do like to throw these on a test to inspire, to instigate, to get students to push themselves. So let's talk about this one in particular. Show that the limit as x approaches negative 2 of 9x plus 20 equals 2. I mean, it's one of the very, very basic limits that we do, right? If you plug in negative 2, 9 times negative 2 is negative 18 plus 20 is 2. Using just our basic limit laws and the practices that we're doing limits, I mean, you can obviously see that the answer is that. But remember, what we're trying to get to here is not just the correct value of the limit, but we want to prove that the limiting process is actually honing in on this value. Okay? So let's do some side work first, right? A little side work. For my side work, what I want to start with is I want to start with the absolute value of my function minus the limit should be less than epsilon. Remember, this is the desired goal. I want to be able to find a delta, an x distance, for every possible epsilon y value distance that we have. So I'm going to, on my side work here, I'm going to work backwards to basically make it happen. Okay, so here I take the absolute value of 9x plus 20 minus 2 to be less than epsilon. By simplifying, I can see that the absolute value of 9x plus 18 would then be less than epsilon. I can factor out a 9, and the absolute value of 9 is still 9. So I'm left with this right here. And then if I divide both sides by 9, I notice that I can say that x plus 2 is less than epsilon over 9. So here at this point, it's a matter of recognizing that x plus 2 is exactly what we need to do. In order to prove the limit right here is equal to something, right? We say that the limit as x approaches some a of f of x is equal to L, means that for every epsilon greater than 0, there exists a delta greater than 0 such that the absolute value of x minus a being less than delta, and of course, being greater than 0, implies that the absolute value of f of x minus L is less than epsilon, right? So we need to go this direction. We need to say, I will always be able to find a delta that implies that my function is within the epsilon distance of the limiting value. All right. Well, like I said, we're working backwards here. So this is what we'll say. Let delta equal epsilon over 9 for any epsilon greater than 0. Then the absolute value of x minus negative 2 being less than delta implies, I'll use the little arrow here for implies that the absolute value of x plus 2 is less than epsilon over 9, which thusly implies that 9 times the absolute value of x plus 2 is less than epsilon, which then implies that the absolute value of 9x plus 18 is less than epsilon. And then I just take one further step here and imply that 9x plus 20 minus 2 is less than epsilon. Okay, so that pretty much proves it right there. The fact that I can start with x minus a being less than a chosen delta for every possible epsilon, and that straight up implies that my f of x minus my limiting value is always less than the epsilon. Therefore, the limit as x approaches negative 2 of 9x plus 20 equals 2, right? Because here's f of x, right? Here's my L, and the x and the a. That goes like these two statements. This statement is now implying that one. And this is the choice right here. Every epsilon, I then choose this calculation to be my delta. So that means it works for every epsilon. I can always find this delta, and choosing that delta implies that this statement happens every time, right? So it's actually saying that for every epsilon that I get closer to the limiting value, I can always find my values in the x-axis that give me those appropriate limiting values. Okay? Next, we'll be moving into the continuity portion, and then also continuity connects us to the last portion with derivatives. So first of all, being able to just look at a function and decide where it is continuous, where it is not continuous. Okay, so again, the only discontinuities that you're going to be dealing with for the most part are places where functions fail, right? Where square root of negative numbers happen, or where divisions by zero happens, or logarithms of zeros and negative numbers. All of those things that are usually called domain exceptions, right? Those are also going to be possible discontinuities. And then, of course, if you have piecewise functions where things are separated. So if I'm looking at this, I'm seeing a couple of things. I'm seeing a division, which I really want to look out where that denominator is going to be zero. But also I've got this square root here, and I really want to make sure and get my domain correct as well. Okay, so I'm going to start by factoring here. I can see that a of x is equal to x minus 7 times square root of x plus 1 divided by x minus 7 times x minus 8. Now, here's one possible mistake that can be made by wiping these out. Don't do that. I have not put this in a limit. It is still a function definition. I have to leave it just like this. Okay? So, the domain of this thing is what I need to list next. Right? My domain. Obviously, I can't do a square root of a negative number. So anything on the negative side plus 1 is going to be a very large negative until you get all the way up to negative 1. Negative 1 plus 1 is 0. I can do the square root of 0. That's where the domain is going to start. So x is going to be an element of, I'll start with negative 1. Next, does it go all the way to infinity? No. Because x can't be 7 and x can't be 8. Both must be excluded. I know what you're thinking. Why can't I just wipe this out? It's a function definition. I can't just take pieces away just because I feel like it's convenient. X can't be 7 and x can't be 8. So the domain is going to go from negative 1 to 7, parentheses, union, 7 to 8, union, 8 to infinity. Now it's all the way out there to infinity. After 8, I have to exclude 7 and 8. Okay. Now let's use our limit language, right? I can tell that there are discontinuities, right? Oh, by the way, I'm sorry, I should have said it. It's continuous on its domain. But be careful. Negative 1, I put a parentheses on. So that's part of the answer right there. List the intervals where it's continuous, right? Describe where it's continuous. Now, why didn't I include negative 1? Because it is continuous, but only from the right. Okay? The limit as x approaches negative 1 from the left of a of x is undefined. So I've only got a limit from the right on a of x. Okay, that's why I didn't include negative 1 as part of the continuity. You could argue it's continuous from the right, but it's definitely not continuous from the left, and so I didn't put it in the whole continuous bunch there. Okay, but it is continuous all the way up to negative 1 from the right. Also, I can see that the limit as x approaches 7 of a of x, okay, is going to be the square root of 7 plus 1 over 7 minus 8. Notice if I put it in a limit, right? If I put this in a limit, I can actually do the reduction. And therefore I can do this calculation. That would give me square root of 8 over negative 1, which is just negative square root of 8. Okay, so notice this limit exists. However, the limit doesn't equal the function value at 7, so it's still not continuous. But what does this mean? X equals 7 is removable. Discontinuity. That's the other description there. Now what about the other one at x equals 8? The limit as x approaches 8. Okay? Now from the left and from the right are going to give me different values. Okay? Let's just pick one of them because that's all it really takes. I'm going to pick from the right of 8. Of a of x is going to be the limit as x approaches 8 from the right of, and I can do the reduction again, it's just square root of x plus 1 over x minus 8. Now here's the thing, if I'm letting x approach 8 from the right, this is going to be a positive number in the denominator. This is going to be some number that gets really close to 3 because 8 plus 1 is 9, square root of 9 is 3. So it'll be 3 over a very, very small positive number. This is going to infinity. The other limit right on the other side would be negative infinity. But this is all I needed right here to show x equals 8 is a non-removable discontinuity. It's non-removable because it's an asymptote, right? It's broken going to infinity, and the other side is negative infinity, but really just one side's enough to show that it's definitely non-removable. The one at 7 is removable because that's just a hole in the graph, right? We call that a removable discontinuity. Okay, so there we have it. We have the few different discontinuities. This one right here is an endpoint technically, so it's not really removable or non. It's just an endpoint, right? So that's what we'll kind of leave that one alone. Next, find a value of k that makes that particular function continuous. So here's my k letter is here, right? You can see k is here. We want this to be continuous everywhere. Well, I'm looking at the function. X is my actual variable here, right? X to the 1. This is a piece of a line. In fact, it's half of a line. It's the left half because less than 2. And then this is x squared plus some number, k. This is a parabola, right? The right half or right portion of a parabola. By themselves, those are continuous everywhere. So whatever piece I grab is going to be continuous for that whole piece. So then what's the problem? The split. The split is the only point I'm concerned with being discontinuous because it's made of two pieces of two very continuous functions. So therefore, I'm just going to find out where these two have to meet up, and therefore it'll be all connected everywhere. It'll be completely continuous everywhere. And that has to happen at x equals 2, right? So in other words, to make this continuous, negative kx plus 2 has to equal 3x squared plus k when x equals 2. I could have just plugged 2 in, that's what I'm going to do next, but I wanted to show the step. These two pieces have to be equal. They have to meet the same y value when the split value, when x equals 2. So I plug in 2 for my x. I'll get negative 2k plus 2 is equal to 3 times 2 squared. That's 12 plus k. Now I've got an equation that's linear in k that I can solve. I'm just going to subtract k from both sides. That's going to give me negative 3k. And then I'm going to subtract 2 from both sides, which is going to give me 10. and then I'm going to divide. So k obviously must be negative 10/3. And then this function will be completely continuous. It'll connect up the proper way, and everything will be continuous. Okay? Now lastly, list the intervals of continuity and use the definition of continuity to explain where these intervals and why they're happening. And then also list any locations where the derivative does not exist and why. So here's our little bridge. We're going to start talking about the connection between continuity and derivation, taking the derivative here. Okay? So just by looking at it, you can see this thing is continuous everywhere except for a couple of points. You can see it breaks right here on this asymptote, and you can see it breaks right here on this open hole there. Okay? So I'm going to say that it has discontinuity at x equals 3. And then it says use the definition of the continuity to explain. Okay? Well, the limit as x approaches 3. We need to give this function a name. How about we call it, let's just go old school, we'll call it f of x here. Right? So the limit as x approaches 3 of f of x is undefined. Notice one side is negative infinity, the other side is positive infinity. Since the limit is undefined, right, then this also implies that the limit as x approaches 3 of f of x does not equal f of 3. And by the way, f of 3 is not defined either. This is the definition that we're interested in right here. And since they're not equal, I have a discontinuity at x equals 3. Okay. Also, I have a discontinuity at x equals 5. Right? And this is because the limit as x approaches 5 of the function is equal to, now look, the limit exists. From both sides, it approaches this circle right here. Let's see, let's number these the way they're supposed to be. Okay? The limit approaches 1. But f of 5, there's a better way to write this. The limit equals 1, but that's not equal to f of 5. F of 5 is 2. Which again, there's the definition of continuity right there. The limit doesn't equal the function value. Therefore, I have a discontinuity at x equals 5. Okay, now, list any locations where the derivative does not exist. Okay, well, the last two things that we just listed, no derivative at x equals 3 or 5. Why? Because it's not continuous. Because no continuity. Right? If there's no continuity, you can't have a derivative, period. That's in the definition. Now, also, there's one more point. No derivative at x equals 1. Because of a cusp. Remember, any sharp point like this, the derivative is not defined at the sharp point itself because the derivative is defined with a limit, and that limit doesn't agree from either side of the values of the cusp. Okay? So I have no derivative at this cusp, no derivative at the split, no derivative at the hole either, because there's no continuity at those points. Okay? Let's finish up with some problems that involve derivatives and its definition. First of all, here's a graph, and it wants you to list the intervals where f prime of x is less than 0. let's break that down. F prime of x right here we're saying is the derivative. And they want to know where it's negative, where it's less than 0. So think back to that definition of derivative. One of the definitions we use is slope of a tangent line. So if you were to draw tangent lines on this graph, wherever the slope of those lines is negative, the derivative is negative. So notice, any tangent line that I draw this way, right? There's a tangent line, slope is negative. There's a tangent line, slope is negative. Where does it change? Right here at this peak, or bottom peak right here. Notice if I draw a tangent line here, it's a positive slope. But then it changes again. And if I were to have tangent lines over here, the slope would be negative again. So I have negative slopes over here, positive slopes in here, and then negative slopes in here. And later on in the course, you'll even see that what we do is we connect the ideas of having a positive or negative slope with being an increasing or decreasing section of the function. So from left to right, I can see that this is decreasing, this is going downward, the slopes are negative, all the way up until -3. Okay, so then that would be negative infinity to -3. And, comma, it goes up, 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 and then notice right here at 1. So it goes from 1, and then it stays negative on out, so to infinity. Okay. So these are the intervals where the derivative is less than 0 for this particular graph. Next, given this function h of x, is the function continuous, differentiable, or both at x equals 2? So there's a little bit of a trick in the wording too that you have to pay attention to. You can't be differentiable only in this case. If you're differentiable, you're also continuous. If you can take a derivative, being continuous is one of the conditions that's necessary for that. Okay, so you're not going to be just differentiable here. You should already know that in the back of your head, like, okay, that's not one of the options here. Okay, you can be just continuous, okay, and you also can be neither, and you can be both, but you can't be just differentiable. Okay, so let's check continuity first, right? Continuity would just be, are these two things equal to each other at the point in question, right? So if I plug in 2, right, 2 plus 2 is equal to, here, -2 squared plus 2 plus 6. So I've got 4 is equal to -4 plus 8, which is 4. So true, it is continuous. Continuous at x equals 2. Now, differentiable means that I should be able to take a derivative limit from both sides as well, and that limit should agree on both sides. So if this thing's going to be differentiable at x equals 2, then I need to be able to take a derivative from the left, which is really just a limit definition from the left, and a derivative from the right, the limit definition of derivative from the right. From the left is easy. You see how this is a linear function here, x plus 2? And remember, derivative is the slope. A line has a constant slope. If you plug something into the definition of the derivative, you're going to get the slope every time. So notice I can already get the derivative from the left, right? So next part, f prime of x as x approaches 2 from the left is equal to 1. Now, what about the other direction? f prime of x as x approaches 2 from the right. This one I'm actually going to have to do the definition for because that's a more complicated function. So that means I've got the limit as, let's do the h goes to 0, right? Not h of x. I've already got h of x here, so let me do a, as little a goes to 0. F of x plus a, so that's negative x plus a squared plus x plus a plus 6 minus f of x. So minus negative x squared plus x plus 6 all over a in this case, right? I'm using a instead of h. It really doesn't matter which one you use. I've just already got h in the name and I didn't want to duplicate there. Okay, so I'm using the limit definition to find this derivative function from the right. So then that's going to be the limit as a goes to 0 of, I'm going to FOIL this out and distribute the negative. That's going to be negative x squared minus 2xa minus a squared. Nothing else to distribute here or here, so plus x plus a plus 6. And then distribute, so that'll be plus x squared minus x minus 6 all over a. X squared and minus x squared. And then I've got plus x minus x plus 6 minus 6. And I'm noticing everything else in here has an a in it. I've got negative 2xa minus a squared plus a. So I'm going to do all of these divisions, right? Divided by a, divided by a, divided by a. So then I've got the limit as a goes to 0 of negative 2x minus a and plus 1. Like that. Okay, which is negative 2x plus 1. So there's my derivative from the right. Now I'm interested in this specifically, what is f prime of 2 as x approaches 2 from the right? Okay, so I'm going to take this derivative function and I'm going to plug in 2. So that's going to be negative 2 times 2 plus 1, which is negative 4 plus 1, which is negative 3. So notice negative 3 and 1 are not equal. So what's happening here? Let's recap. We found that it is continuous because the y values are the same. So the functions meet up. But the slopes, the derivative measuring the slope is different from the left and from the right. So you're getting a cusp, a sharp point. One of them has a slope of 1, the other has a slope of negative 3. So you're getting like this sharp point where the two parts meet up. Okay, so with these two being different, continuous at x equals 2, but not differentiable at x equals 2. Okay, lastly, find the equation of the tangent line to the function curve at x equals 4. So we have a function, we have an x value, and we want to find that tangent line at x equals 4. Okay? So first and foremost, I mean, we just got to remember what it takes to create any kind of line, right? I'm going to use the point slope form, y minus y naught equals m x minus x naught, right? I've already got the x naught, which is going to be 4. So I'll do a little bit of side work over here. I know I've got this much of this equation. I know that I have this much of it. So next, what do I do to get the y naught? Well, y naught is going to be equal to c of 4, just the function value, the y value at 4. If I plug in 4, 13 minus 4 is a square root of 9, which is 3. So I've got that value. I've got my x and y value for the point of tangency. That's the point where the tangent line is meeting the actual function. Lastly, to get my slope, I need the derivative because it says tangent line. The derivative is what's going to give me the slope of that line. So I'll make the derivative and then I'll plug in 4. Okay, so c prime of x is going to be the limit as h goes to 0 of f of x plus h. So that's square root of 13 minus x plus h, like that. Minus f of x, which is going to be the square root of 13 minus x, all over h, like this. Okay. Now, that is going to be equal to limit as h goes to 0 of. What I'm going to do is I'm going to multiply the numerator by its conjugate. That's what you do to make the numerator sort of simplify out. Okay, so I'm going to start with a parentheses, square root 13 minus x minus h. Notice I just put the negative into both of these two things here. Minus square root of 13 minus x times its conjugate. That's going to be square root of 13 minus x minus h plus square root of 13 minus x. Notice it's identical, right? Except it has a plus instead of a minus. And then in the denominator, I will simply be multiplying the same thing. Like so. That makes it legal. I'm multiplying the top and bottom by that conjugate. So I've got limit as h goes to 0. Multiplying this conjugate, I'm gonna be able to keep the surviving elements of the first times the first and the last times the last. Notice the cross terms, the square root of 13 minus x, square root of 13 minus x minus h, and same thing, multiplication here. But one of them is positive and one of them is negative. Those are going to add out to 0. What I will keep is this radical times that radical, which is just 13 minus x minus h. And then this radical times this one. So that's going to be 13 minus x. But be careful. Negative times positive in that two last ones. So it's actually minus the whole thing. All over h times, and I didn't really do anything to the denominator, you'll notice. I don't need to. Now, if I distribute here, note that what I will get is 13 minus x minus h minus 13 plus x. So the 13s are going to add out, and the negative x and the plus x are going to add out, leaving me with a negative h. Negative h divided by just this multiplied h right here is going to leave me with a negative 1 in the numerator. So now I have the limit as h goes to 0 of negative 1 over square root of 13 minus x minus h plus square root of 13 minus x. Notice now I can let h go to 0. Okay, this piece will go away, and I simply have two of these radicals that are identical to add together. So my derivative function here is negative 1 over 2 square root of 13 minus x. Okay. Now that I have my derivative function, what I'm actually interested in is a slope for my tangent line at x equals 4. So this is c prime of x. Therefore, c prime of 4 is negative 1 over 2 times the square root of 13 minus 4, which of course 13 minus 4 is 9, square root of 9 is 3, 3 times 2 is 6. So I have negative 1/6 for the slope at that location. All right, so let's finish up the problem. They want the equation of the tangent line. That's the slope of the tangent line. So negative 1/6 then goes here. I have y minus 3 equals, I'm going to distribute. 4/6 is 2/3. I'm now going to add 3, which is 9/3, right? Plus 3 is the same as plus 9/3. So that's going to leave me with y equals negative 1/6 x plus 11/3. And there's the equation of my tangent line. So I hope these problems help you in your efforts to prepare for your first calculus test. As I said at the very beginning, don't focus on individual problems and don't expect them to be exactly the same. All of these skills are things that can be applied in many different ways and read in many different ways and thought of from different directions. Practice these problems, practice some other problems from your textbook, do whatever else it takes for you to see the skills that it takes to do these problems, to piece them together. Don't just memorize these particular problems.